Thank you so much. You may start whenever you want.
Okay. Yeah. Thank you very much, Dr. Isabel, for the introduction. And it's my pleasure to join this presentation at this time. My outline for today is going to be, I just talk briefly about myself, and I'm very grateful to Isabel for the introduction. So I'm just going to skip that, and I move to talk about my teaching strategy and talk also about my research. In my research, I'm focusing on catalysis for the mitigation of climate change. And in this area, I'll be talking about two strategies. One of the strategies is to minimize the amount of greenhouse gases to the atmosphere. The second strategy is to mop up the existing greenhouse gas in the atmosphere for a kind of circular economy to produce useful chemicals. I don't need to talk about my teaching education that has been done by Isabel and my work experience. So far, I have about 3 PhD students that have passed through me. I have 4 MSc students that have trained and a number of undergraduate research and plan design projects. I also initiate and supervise a number of students in engineering team projects where we have engineering students from different departments, from chemical, civil, mechanical, electrical, coming together to work on the same project. I did this in Malaysia, and when I was a visiting professor in Canada, I have published a number of new papers, from single author paper to a number of co-author papers. In my teaching, I have embraced the concept of constructivist pedagogy, which is simply creating a classroom environment, activities and methods that allow each student to learn at their own pace. And I do this to help the student to construct their own knowledge through experiences, activities in the class. And I love to focus on teaching the fundamentals of scientific or the engineering fundamentals in all the courses that I've taught. And I have some experience in the industry, and I also consult for industry. So I love also to talk to students about the industry application of the concepts that I'm teaching. Then I love to introduce the concept of process design, process simulation using Aspen. And today I'm going to show you one example of that, and also introduce the concept of research in some of my taught courses to give the student a deep feel of the course. And in any course I taught, I love to get a reflection from the student, for the student to give me some feedbacks, answer some basic questions for me to know if they are learning. These are some of the courses that I've taught, and if you look through, you will see that these are some of the core chemical engineering courses, from separation techniques to thermodynamics, fundamentals of process plant design, chemical reaction engineering, and so on. In all the courses that I've taught, like I mentioned, I love to teach with relevant software because we are in the computer age. It's not enough to understand the concept in theory. It's also important to be able to use computer application to solve some of these problems in the 21st century. And some of the courses that I am proposing, developing presently, what I have here, I have computer-aided gas process engineering. This course is very important to me because if the shift from fossil fuel, from oil to gas, and is making gas engineering more interesting and popular again. So I'm developing a course for gas process engineering. I also developed a course, piping and mechanical designs for process equipment, to be taught alongside the plant design chemical engineering curriculum. And also developing a course in fundamentals and applications of nanomaterial, specifically in nano devices, catalysis applications. If you look at this example I have here, this is one of the slides I taught when I was teaching distillation in separation techniques. We teach students basically to look at the top operating line, the bottom operating line. We use all this to calculate the number of stages in the distillation column. But the current requirement in engineering goes beyond doing this McCabe and TL method to calculating the number of trays. Students need to understand if the purity, for example, in the top stage is increased, let's say I'm moving from 90% purity to 99% purity, what happened to the number of trays? If I increase the reflux ratio, what happened to the number of trays? If I increase the pressure in the condenser, the pressure in the reboiler, what happened to the number of trays? And that is what I'm showing in this simulation we have here. Please, do you have my simulation screen?
Yes, I think so.
Yes. Yeah.
Thank you very much. So having taught this concept in the classroom, I also use my simulation to dig deep into this concept. If you look at the HSG, the distillation column I have here, basically what we teach students in the traditional class is to determine what is going to be the minimum reflux, which is dependent on the component in the key, the top component, the purity at the top, the purity at the bottom, depending on the composition of the feed. But what happens if this reflux ratio increases? And that is what I show in this simulation here. What happens if the temperature of the feed increases? What happens if the key component in the bottom is increased to have high purity in the bottom? How does it affect the efficiency of the cooler? How does it affect the return liquid from the top that is condensed from the condenser? How does it affect the reboiler duty, the work done by the reboiler to keep heating the condensed liquid? And that is one example I have here. If you look at the graph I have here, which is from this distillation simulation here, this shows that if the reflux ratio is increasing, then the number of trays is reducing. If the feed temperature is increasing, for example, up to from 20 degrees to about 90 degrees, there is no change in the number of trays. But slightly above 90 degrees, there is tremendous increase in the number of trays. So this will generate question in the mind of the student, because this is graphical, this is simulation. It generates question, and to understand or to explain what is happening in this region, they have to go back and check the composition of what they have. In this case, I have composition of benzene and toluene. Then we need to understand what is the boiling point of benzene, what is the boiling point of toluene. So it means up to this point, there is no change in the Q line, which is what we have here. This Q line is what is affecting that straight line we are seeing in the simulation, because the Q line is not changing because the feed is still below the boiling point of the feed. So temperature changes, increment remains the same. There's no effect on the number of trays change. But when it comes to the boiling point of benzene and toluene, then this is changing the Q line. So with this, you see that a student really understand when you talk about the concept of Q line. When I was a student, I wasn't taught this way, and I don't really understand what is Q line. Feed at boiling point, feed saturated feed, saturated temperature, and so on. But with this that I am using, the students are able to carefully and critically say, again, if I increase the reflux ratio, what happens to the stripping liquid, stripping vapor? These are increasing. What is the implication of this in plant design? It means there's going to be more work to be done by the reboiler and the condenser. So students understand when you're talking about operating costs and capital cost investment in plant design. Another simulation we want to see is the effect of the reflux, for example, on the reboiler duty, the energy in the reboiler. So as the reflux increases, of course, the reboiler energy increases. But this is an advantage because we have high purity at the top. So a student can do this simulation to be able to optimize, to be able to strike an economic balance at a point where he can minimize the energy in the boiler, at the same time maintain high purity at the top of the distillation. And when I taught optimization, process optimization, that is what we have here. I have the product coming from the same distillation to preheat, heat exchanger, to preheat the feed that is going into the heat exchanger. So in this case, I'm not only teaching the concept, I'm not only teaching the fundamentals, I'm also showing the student how process design is done and how this is actually practiced in the industry. Now, why am I so concerned about this? I've been involved in the past in my previous university in curriculum development, and we are looking at the changes in engineering requirements. For example, if you look at 2015, the top 10 skills for engineering students involve complex problem solving, critical thinking, negotiation, and so on. 5 years after, in 2020, complex problem solving skill is still needed. Critical thinking is still needed. No student can do critical thinking. No student can do complex problem solving if they are not involved extensively in simulation, where they can see the deeper picture beyond really the textbook. And if you look at 2025, the future, it's about 2 years from now, requirement, this is according to the World Economic Forum, the first requirement here is analytical thinking and innovation. This is reinforcing the need for the student to have deep understanding, deep appreciation of complex engineering problems, which can be aided using computer simulation. And you look also there, we have active learning and learning strategies, complex problem solving is still among the first top 10 skills for 2025. And if I show you a sample of my student work, if you look at the sample of this student work, I gave a problem on gas process engineering. This is a student work, and they have about a week to solve this test. Now, if you look at what they did here, the student have to first of all write from the introduction. The solution to this test is like a research paper. Like I mentioned in my teaching pedagogy, I integrate a kind of simulation, research, and fundamentals into the courses. So the student have to write an introduction, have to write the methodology, and see the student doing the simulation and interpreting the result. And this also gave me opportunity to give some feedback to the student. Since these are some of the student work, the simulation of 3 different types of 3D plots. We're looking at effects of, for example, in this case, the student is looking at effects of temperature and pressure on the compressibility factor Z. In this case, it's looking at compressibility factor as a function of temperature, as a function of pressure, and the student can write discussions that I can give some comments on the discussions to help the students improve in their fundamental understanding and also introducing them to doing some elements of research in my course. So this is just to summarize some of the concepts in my teaching strategy. In summary, I love to put in the fundamental science and engineering concepts. I love to introduce simulation into it, and I love students to do some elements of research, write some papers from the assignments that I've given to them. Now, I'm coming to my research. My research, like I've mentioned, is just an interplay between chemical engineering, nanomaterials, and catalysis to solve climate change problem. Because of that, I integrated some concepts from thermodynamics, from catalysis, from process simulations, and with nanomaterials, synthesis, functionalization, activity measurement, and characterization. Of course, they are no longer nailed the reality challenge that climate change is the greatest threat to humanity. it affects human health, it causes heart attacks, it increases chances of strokes, and so many other infectious diseases. This climate change coming from greenhouse gases, especially from CO2 and CH4 that my research have focused on. These CO2, CH4 are coming from flare gases, coming from exhaust of airplane that pollute the atmosphere. And when I saw this last year or 2 years ago, it is shocking to me to see that before COVID, there is about 16.1 million flights in 2019. And this is producing about 1 billion tons of CO2. So if we imagine 1 billion tons of CO2 every year in the atmosphere, this is a calamity for the future. Unfortunately, these numbers are not expected to reduce anytime. They keep growing because human being keeps moving around. There is increase in population. Another menace is from methane, which in fact, studies have shown that it is 6 times more powerful than CO2 gas in a period of 20 years. And it can stay in the atmosphere for about 12 years. So I look at this and try to develop a research around this. What are the impacts of the climate change? The first and the most critical that attract my attention is melting of the global ice. The consequence of this is flooding. Virtually every part of the world has been affected with flooding, ranging from India, in Asia, in China, to in Europe, in Germany, in Syria, in Bangladesh. Even here in the United States, we are suffering from the same menace from climate change or flooding. In Tennessee, where I worked last year, and I saw also even in Coimbra in Portugal, it's not spared from flooding. Some places in Lisbon in 2022 December, they flooded. Even in Porto, this is calamity. You see, this is happening. So what I do is to innovate my own strategy to clean up the existing CO2 by developing a system that can capture CO2. There are different strategies that have been developed for capturing CO2, some captures and sequestrate and utilization. In utilization, we have conversion and non-conversion for enhanced oil recovery. So for me, I focus on conversion to produce different specialty chemicals. And the first project that I developed is to have a kind of continuous nanoparticles to capture CO2 from flue gas. This concept is to replace the traditional imine solution. Instead of having a mine flowing in the absorption system, what I have there is some nanoparticles that are functionalized to be able to have high affinity for CO2 capturing and also high ability for desorption of CO2. So the CO2 capturing is captured in the cold, in the low temperature region, and it flows into the hot temperature region where it desorbs the CO2. The CO2 can be conveyed into a reactor system that can convert the CO2 into specialty product in situ instead of capturing and storage. In terms of conversion, my latest finding in this area is to develop a catalyst functionalized with different functional groups. So I have a copper-based catalyst that was supported on zeolite. The same catalyst was functionalized with sodium borohydride, and another catalyst was functionalized with oxalic ligands. So what is the difference here? This is having an borohydride functional site, and this is having an oxalate ligands around it. So for conveniency, we call this non-functionalized. I will call this guy CUB, and I will call this guy CUX. Now, if you look at the textural properties and morphology, there is significant variation that is so interesting to look at. For example, if you look at the oxalate functionalized, the CUX, the hysteresis lobe that was closing at about 0.42 here opens up to about 0.1 here, and I'm going to explain the implication of this. And if you look at the morphology here shows the particles have lost some crystallinity compared to the starting material, which is the zeolite Y. For the borohydride CUB, this has transformed to some foamy material, and I suspect that this is due to the evolution of this hydrogen gas during the synthesis of the catalyst. Another interesting feature I can see from there is this with CUX, with oxalate, has lost the micropore, and I'm going to talk again about the implication of this. The micropore have disappeared, the micropore volume have also disappeared. Now, if you look at the pore structure, the CUS has lost completely the micropore, while the secondary pore reduced. However, for the CUB with borohydride, there is growth, there is increase in the secondary pore here, and I'm going to talk about this also later on. And when I look at the TEM imaging to look at the particle sizes, you can see that the effect of the functionalization with borohydride and oxalate significantly impacted on the particle size and the particle size distribution. Whereas we have the unfunctionalized, a very large particle, about 8.3, and the functionalized is about 1.4 and 0.9 for CUX and CUB respectively. Now, this generates some curiosity that I want to see what is happening on the functional group on the catalysts that are synthesized. The first interesting feature here is to look at this peak 1190, which has been ascribed to pore opening vibrations. If you look at the peak disappeared nearly completely in the CUX, while the peak increased significantly in the CUB. So when I take that to the pore structure, you can see that the CUX has lost the micropore and the secondary pore has significantly reduced. So this is an agreement with the FTR result. For the CUB, there is increase in the band here, and that can be ascribed to this increase in the pore structure. As you can see, it has moved even to a higher pore diameter. Another interesting feature I found from there is the loss of the alumina in this pore at about 666 centimeter to power 1 here. That is why we have this band flattening out. And this is due to de-alumination. Typically, when aluminum silicates like clay and zeolite undergo acid treatment, depending on the degree of acidity, they have varying extent of loss of extra framework alumina, which removes the alumina in the extra framework. And that's, to really confirm this, I have to check the XRD. And if you look at the XRD, you will see from here that the zeolite Y characteristic peaks have completely disappeared in the sample that was modified with oxalate, which means there is protonation effect that has caused significant de-alumination that transformed the material from crystalline to amorphous. Another interesting feature I found from there is the basic site of this catalyst after synthesis and character and calcination, which have pushed both the weak and moderate basic site, the strong and very strong basic site in the modified CUX and CUB structure. Calculating the total basic site density, it is obvious from here that the CUX has the highest total density, which is followed by CUB. And I'm going to show the implication of this on the activity and selectivity of the catalyst. Another interesting feature which really interests me is the reducibility. Typical reduction pattern for copper should go from 2+ to Cu plus and to Cu metallic. So these two create the two peaks of alpha and beta. If we look at the unfunctionalized, we have the alpha and the beta. For the oxalate, for the CuX, you see that the first peak is significantly reduced. For the oxalate, for the borohydride, the first peak completely disappeared. And the implication of this is the downsizing of the particle size to very small particle size that can be reduced in a single step. And that is why we have seen here the particle size here is quite small, far lower compared to the particle size of the unfunctionalized catalyte. And of course, this leads to the increase in the dispersion and the number of active sites that are available for reaction. Now, I look at this in terms of the activity of this catalyst. How does this characterization results impact on the activity of this catalyst? If you look at for the CUS, it shows the highest conversion of CO2, and that was ascribed to both the downsized particle size at the same time as a strong basic site, which allowed the acidic CO2 to be absorbed for activation at the catalyst active sites. Then also I look at the selectivity of the catalyst. Interestingly, the catalyst that was functionalized with borohydride produces more of DME, dimethyl ether, while the catalyst that was functionalized with oxalate produces more of methanol. So I was curious to understand this concept. One of the things I found from there is dimethyl ether is a relatively complex structure compared to methanol. So having this, the increase in the pore structure appears to help the dimethyl ether to be able to move through the pores, which is not in the case of CUX, because the pore in the CUX are actually very small that cannot permit the large molecules like dimethyl ether. Then I look also trying to understand why the CUX, even though it has a larger, higher dispersion, smaller particle size, the conversion on the CUB is low compared to the conversion on CUX. And one of the things I can ascribe that to is the formation of this bond, which is CUB, copper borohydride, that may not be reduced under hydrogen reduction, which was also seen in the SPL. So even here, we have the copper borohydride peak. So the details of this have just been published in this journal late 2022. Another work that I worked on, which is based on the amount of CO2 in the atmosphere, the strategy this time around is to reduce the weight of the airplane. If the overall weight of airplane can be reduced, then the fuel consumption can be reduced. And some companies have claimed they have saved about 5,000 on fuel by replacing some non-critical metals in the aircraft with polymers, which makes the weight of the aircraft lighter, consume lesser fuel, produces lesser CO2 in the atmosphere. So to achieve replacement of this, there is need to produce or increase in polymer production. Prior to now, polymers are used in all of these areas. So we need more, excuse me, we need more ethylene as the feedstock, the monomer of polymer to produce more ethylene. And that is putting a pressure on the ethylene market. If you look at what I have on my screen, just within about 10 years, the price of ethylene is nearly double from $176 to about $287 by 2030. But in a way to ease the pressure on ethylene market, then there is need to improve the production of ethylene, bring down the cost, understand more the fundamentals, the theory, the science, and what can be done to actually improve production of ethylene. When I was at IML in Braga, in Portugal, this is the project I worked on, which is trying to remove acetylene from ethylene. In the process of producing ethylene by cracking of naphtha, we have some acetylene that is produced in low quantity. Even though it is low as 3 ppm, the acetylene can poison the Ziegler-Natta catalyst of polymerization. Therefore, there is need to remove the acetylene from the ethylene stream. There are two strategies: is semi-hydrogenation or to use membrane. But because of the large volume of the feedstock to be handled and the low concentration of acetylene, the best method to go with is semi-hydrogenation. However, the main challenge in semi-hydrogenation is thermodynamic functions. At high temperature that is required to convert the acetylene to ethylene, conversion of ethylene to ethane is even more favored because this is more endothermic compared to the primary process of acetylene semi-hydrogenation to ethylene. And if you look at one of the results from the literature, you see that as conversion increases, the selectivity to ethylene reduces. So a good catalyst should be able to maintain reasonably stable selectivity even at high acetylene conversion at high temperature. So strategies have shown that the best way to do this is to move away from thermodynamic, to move away from process manipulation, to move to catalysis manipulation. And that is what we are doing. To achieve this, the secret we found was to bring down the D-band center of the catalyst downward or Fermi level. And to achieve this, if we downsize the particle size, this can be safely achieved. And the smallest part downsizing particles we can have is to have a single atom. So we explore different strategies, starting from the DFT computation to gain an insight into the semi-hydrogenation of acetylene concept and develop a catalyst based on our DFT calculation and predictions that can be tested. So we use a technique known as the flame spray pyrolysis, where we have the organic precursor of the catalyst, active metal, in this case platinum, and the precursor of the support that are combusted together to produce the catalyst. So we have different catalysts. In this case, we have Syria, which is the virgin support without platinum. We have 0.23% platinum, we have 0.5 platinum, we have 5% platinum. And as the platinum loading increases, you can see the color changes. One of the first interesting things we found in this result is from the TPR. If you look at the bulk oxygen of the Syria, it was on at top throughout the loading of the different loadings of platinum. But if you look at the surface oxygen, there is migration of the surface oxygen peak to lower temperature as the particles, as the platinum loading reduces. This is the 5 weight percent, this is 0.5, and this is 0.23. The interesting picture here is we found that the peak of platinum has actually merged with the surface oxygen peak of the Syria. So in a kind of changing the surface chemistry, which looks like in the 5 weight percent, we have platinum oxide sitting on Syria. However, in the 0.23, the platinum oxide is strongly interacting with the Syria such that both platinum and Syria are sharing one oxygen atom. So it appears from this peak that as the platinum peak is moving towards high temperature, we have the surface oxygen of Syria moving towards low temperature. And this is based on the concept of the weak metal support interaction, strong metal support interaction for the low and high metal loading. Then we check the SPS, which confirms our hypothesis that the 0.23, the peak of platinum, you see this shifting towards higher binding energy, while the peak of platinum in 5 weight percent is shifting towards lower binding energy. Of course, the 0.5 is standing somewhere in between. So based on this, we are curious to check what is the diffraction patterns in the TAM, the high resolution TAM of this catalyst. For the Syria, the diffraction pattern conforms as expected with CEO2, Syria 4. But when we look at for Syria 0.23, we have this Syria 2 oxygen to 3, which agrees with what we have in the TPR result that confirms there is a strong interaction between platinum and Syria support. And when we check for the 5 weight percent, the Syria exists in a Syria 4 oxidation state. This increased curiosity in now that we have to run yields analysis to check. So if you look at the yields of the 0.23, it conforms with what we have in the diffraction pattern and the TPR. It is C3 plus. For the 5 weight percent, it is CE4 plus. Then we try to eat up because in the TEM image, we are able to find traces of platinum at the 0.23. So we eat it up to study what happens as temperature increases. Interestingly, we found that as temperature was increased to high temperature, the oxidation state in this catalyst changed from 3 plus to predominantly 4 plus. And when it was cooled down, it maintains 4 plus, which means the particle sizes here are agglomerated and grown. To prove this, we take the the TEM image as we heat it up to high temperature. And you can see that we are unable to see the particle of platinum before eating, but after eating, there are particles of platinum, which show that the platinum have agglomerated, sintered to form larger particle sizes. And with this, we are curious to check the regime of the particle size to see if this is single atom, if it's nanocluster, if they are nanoparticles, and the rest. So we run the drift analysis to look at the particle size regime to confirm what we have seen so far. For the 0.23 weight percent, which is the black line, we have this peak, which is 2094, and this peak has been assigned to linear CO or an atomic PT. So we can say that we have an atomic dispersion of platinum on 0.23 weight percent, and we have very large nanoparticle sizes of varying sizes on 0.5, on 0.5 and 5.0 platinum Syria catalyst. Then we test the activity of this catalyst on very low amount of acetylene in large amount of ethylene, which is a typical industrial configuration. We denote conversion with X, S by selectivity, and yield with Y. For the 0.23 weight percent, we have reasonably stable ethylene selectivity, which is the blue line. We have reasonably stable ethylene selectivity, even at very high temperature. We still have about 80, but still 80% of selectivity. However, for the high loading platinum, as the temperature reaches about 120 degrees C, you can observe that the selectivity, the blue line of ethylene, has completely gone to negative. Negative in this case means both the acetylene in the feedstock and the ethylene in the feedstock has been converted to ethane. This confirms that this catalyst is not good for semi-hydrogenation, and this is one of the sheer providences in science where we have low platinum loading, giving us the desired result because platinum is quite expensive. So using very low amount of platinum, we can achieve what we want in semi-hydrogenation, and we can produce more ethylene that can support the production of more polymers that can be used to replace non-critical metals in aircraft by reducing the overall weight. Some of these are what I've shared have been published in these papers. And lately, I was curious again to look at replacing platinum copper with platinum cobalt. So we synthesize again platinum copper catalyst, platinum cobalt catalyst. We look at the TEM imaging. It appears from here the platinum copper, the particle sizes are quite smaller compared to the particle sizes of platinum cobalt. And we check also the TPR imaging result to look at the reducibility. One interesting feature from here is the multivalent peaks that should be seen for reducing from M2 plus to M plus, M plus to M naught cannot be seen here. If you take this to what I've shown previously in the CO2 hydrogenation TPR result, having one peak is an indication of highly downsized active metal particle sizes. So in this case, it appears here that the particle sizes are quite small, but we need to know how small are these particle sizes. To check also the XPS of this catalyst, one of the interesting striking picture here is we observe that the platinum cobalt, the platinum in the platinum cobalt catalyst is shifting more to higher binding energy than the platinum in the platinum cobalt. This shows the strong beta support interaction in platinum cobalt catalyst is higher than that of platinum cobalt. And I'm going to show more on this. So we test the activity of this catalyst. We are interested in the yield of ethylene. We look at the yield of ethylene on the platinum cobalt catalyst, which is the figure A, platinum cobalt catalyst. At about 120 degrees C, we have the maximum yield of ethylene. Beyond that, ethylene yield start going down. However, for the platinum copper, the ethylene yield increased monotonously even until about 200 degrees centigrade. And at that point, we have the complete conversion of acetylene. However, in this case, we are not able to achieve complete conversion because of the competing reaction. Acetylene going to ethylene, ethylene going to ethane. So this impedes the first reaction, which is less thermodynamically favored. Now with this, we are curious to understand this phenomenon. Why is this favored? We are interested in knowing what is the local platinum structure as this reaction proceeds. So when I was in China on a fellowship, I used the opportunity to run a cyclotron study at the Shanghai cyclotron facility. And I saw very interesting features in this catalyst. If you look at this platinum foil reference material, the platinum oxide reference material. Now, this is the platinum cobalt as prepared. AP stands for as prepared, this and this denotation here. This is platinum cobalt with hydrogen reduction. This is platinum cobalt. This is platinum copper as prepared. This is platinum copper under hydrogen reduction. And ESP is under experiment. Now, if you look at the platinum cobalt as prepared, there is still significant oxidation, PTO bond. There is still significant amount of PTO, which means there is still there is less instances of platinum cobalt alloy. But if you take a look at the platinum cobalt as prepared, platinum copper as prepared, you see that the feature of this platinum oxide is missing. The fixture of platinum foil is missing. Two things are suggested here. The first thing is the particle sizes are quite downsized, which is in agreement with what was shown in the TEM imaging. The particle sizes are quite downsized. Two, there is significant extent of alloying between platinum and copper in the SPPA catalyst compared to the platinum cobalt in the SPPA catalyst. That is one take home. The second information there is during reduction, as expected, the peaks of the platinum oxide have disappeared, they reduced. So we have platinum metal. But if you look at platinum cobalt, after reduction during experiment, there is still changes in the spectra, which suggests that these platinum cobalt catalysts are actually not stable under reaction. However, if you take a look at the platinum cobalt and copper, during hydrogen reduction and the red line under experiment, you see that the spectra is almost the same thing, which shows that this catalyst is quite stable. So this stability of this catalyst is quite partly responsible for the selectivity of ethylene that we want, because it is strongly alloyed. The platinum and copper are alloyed, and that is why we have a strong metal support interaction we saw in the SPO. And to confirm that, if you come to the CU and the CU edge and the CO edge, you see that the platinum copper as prepared catalyst, the signature is complete, is a complete departure from the signature of the reference material of CU4 or CU1 or CU2. However, if you look at the cobalt, you see that the cobalt still maintains significant signature of oxidized cobalt 3, and that is why the extent of alloy is low in the platinum cobalt, and that is responsible for low ethylene yield over the catalyst. We also check the zincs of this catalyst, and the result is also the same thing. One important feature that I would like to talk about briefly on the zinc features is what I call the first order differential absorption spectra, which is differentiating this spectra in the first order. You look at the PT energy here is about 11,566.8, which is quite far higher compared to what we have for platinum cobalt under experiment. And this finally seals the argument that there is strong alloying and there is strong metal support interaction in the platinum cobalt, and that was what was responsible for the significant stability and increase in the yield of ethylene selectivity as compared to platinum copper. Now, the last thing I will talk about briefly on this semi-hydrogenation is I use the platinum on serial catalyst that was not giving good result because the platinum loading is high, which is 5 weight %. I dispersed it in those catalysts I showed earlier that I use for for CO2 hydrogenation. Whereas the catalyst for the CO2 hydrogenation is now serving as the support, the copper functionalized catalyst is now serving as support for platinum, and I tested it again under semi-hydrogenation. So what I did was to put the platinum serial catalyst 5 weight %, disperse in ethanol, and silicate this with the zeolite catalyst, and dry this, filter dry this, and calcine, and denote this as PTCE, Cu zeolite Y. I did the same thing for the other copper borohydride and copper oxalate catalyst, and support the platinum onto this catalyst. Then I test the activity of this catalyst again. Amazingly, the air stability feature shows there is significant composite development of composite in the new catalyst. And when I check this, the stem ears images to look at the extent of alloying or perfect mixing, if you move from the first one, which is the platinum on Syria, this is the number C is platinum Syria on copper catalyst no functionalization. You observe that the mixing of the Syria, copper, and platinum is very poor. There is segregation of platinum. But for the copper oxalate and the copper borohydride support, there is near perfect mixing of platinum Syria and copper, and platinum Syria and copper. So this shows a reasonable extent of alloying, reasonable extent of perfect mixing that can support the semi-hydrogenation of acetylene to ethylene. We check the reducibility pattern of this. The interesting picture I would like to show here is, this is the platinum Syria from the SPS. You see the peak, before the peak here is, as I disperse this platinum Syria on zeolite white support, this peak is gradually reducing. The peak at the 4F72, this peak is gradually reducing. When I introduce the copper into this peak, into this catalyst, this peak reduced more. When I functionalize this with oxalate, the peak reduced more. And lastly, with the oxalate, with the borohydride, the peak drastically reduced. The implication of this is the particle sizes are getting smaller, and as they get smaller, shifting towards higher binding energy implies that they are strongly interacting with the support. So I checked the D-band center for each of these catalysts, and I observed that with each modification, the D-band center is lowered, is brought down relative to the Fermi level. However, because the shapes of these D-band are not the same, they have different shapes, even though we're able to determine the D-band center, I was motivated to check the upper D-band edge, which is differentiating this spectra to the first order. Differentiating this gives me the upper D-band edge, which now makes the spectra looks almost the same shape relative to the D-band shape here. So with this, I can now take the value of the upper D-band edge, and for that, I can see that for the platinum Syria, the upper D-band edge is positive, and downward, the value goes to 0.4 in platinum Syria and copper. When it was functionalized, the value goes even to negative. What is the implication of this? The implication of this is, as values go to negative, I'm able to produce more of ethylene, because it means the adsorption energy of ethylene on the surface of the catalyst active sites is weakened, such that when acetylene is hydrogenated to ethylene, it has the ability to dissolve away from the active site. And this prevents subsequent hydrogenation into ethane. And that is what you see in the result here. This line with the circle, the empty circle here, is for ethylene selectivity. You see that on platinum Syria, the ethylene selectivity is negative, everything goes to ethane, which on support, on zeolite, it gets a bit improved. With copper, it gets a bit improved. With oxalate and borohydride, the improvement becomes significant. And I try to summarize all this in this quadrant. So we have the good catalyst in the first quadrant, where we have the positive ethylene yield, we have high ethylene yield. In the second quadrant, we have intermediate ethylene yield, whereas in this third quadrant, we have zero ethylene yield. In fact, we have depletion of ethylene in the feedstock to ethane. Another strategy that
sorry to interrupt you. My colleague Isabel has another meeting, so I'm also vice president of the department. And I'd like you to ask you if you can go to your conclusions because we are reaching the end of the slot. Can you hear me?
I can't hear you clearly. The voice is not clear.
Okay, sorry. We are reaching the end of this DEQTalk. Can you go to your conclusions, please? Because we have a slot of 1 hour for this. Sorry.
Okay, yeah. I will have to stop at this junction, therefore, and I'll be happy to take some questions.
Okay. So thank you for your presentation. That until now it was quite interesting and showing that we are researchers. And so, if some of colleagues have any questions or comments to Olumide?
Yeah, I can hear you, but it's not very audible. I think your microphone is covered somehow.
So let me change the microphone.
Is it better now?
It's excellent.
Okay, so I'm saying that my colleague Isabel have another meeting, so she need to left. But if there is some questions or comments to Professor Olumide from our colleagues, please go ahead.
Just one question. You spoke about this flame spray pyrolysis method for the catalyst preparation. And we know, of course, that in a flame, each droplet will suffer different temperature profile. And of course, do you recognize that the homogeneity of the final catalyst is very high, or there is some part of it which is with different composition?
Yeah, thank you very much. From the sample we have a reasonably homogenized particle size from the morphology, and we try to run the ICP, taking the samples at different points, and the values we have, the variation is still within acceptable scientific range.
And do you know any industrial application of this method for the preparation? Do you, let's say the question in another way, is it a process which is now at TRL 3 or 4 or 5, but do you know any industrial application of this process?
Okay, for now, I am not sure of any company or industry that is using this, but from a background in process engineering, I strongly believe this is a process that can be easily adapted to industrial because it's a good continuous process with high throughput. So I feel it can be easily adapted to industrial practice, but to be honest, I cannot mention a particular company that is using that for now in large-scale production, except thesis in Italy. It's a spring-up business that is still at the infant stage. That is, in fact, they are the one that prepared these samples for us, but it's still an infant stage business.
Thank you.
Yes.
Any other questions or comments?
Yes, can I ask one?
Yes.
Yes,
I
of course.
I'm more interested in knowing about your career perspective. So you are currently an associate professor in Texas. So why this interest in coming to Portugal and for the chemical engineering department? Can you explain a bit about your goals and what you are expecting from us as well in terms of your career development?
Thank you very much. As Dr. Isabel mentioned in the introduction, I have lived and worked in Portugal, and I love everything about Portugal. In fact, I had a baby in Portugal, and I don't really want to leave, but when my tenure was over at INL in Braga, I have to come back to the US to continue my work here. But to be honest, I am so impressed with the number of the institutes and centers that you have in IST. I have noticed because unfortunately, I'm not able to show my work on plasma catalysis. I have done a reasonable amount of work in plasma catalysis. And when I look at your center in IST, it appears that virtually everything that I need for my research in plasma catalysis at your Institute of Plasma and Nuclear Fission, I look at the material processing and characterization. Virtually everything that I need is available there. And if you look at the area of plasma, I'm trying to bridge plasma and catalysis. This is not a very popular area. So getting facilities, getting collaboration, working together in most institutions is challenging for me, especially in Texas here. There's nobody that is presently working on plasma or plasma catalysis. So when I look at your Center for Plasma, this, if I'm given the opportunity, I have a good springboard to start my research, because most of the facilities, especially the high-end facilities, are present at IST. So it's one of the reasons that make me feel interested in applying to IST. And I still have some opportunities to use some facilities in Braga because I'm an alumni of INL. So if I have the opportunity at IST, I can also continue some of my projects at INL in Braga. So coming back to Portugal, for me, it's going to be like coming back home, where I can continue my collaborations with people that we have worked together. And again, specifically, I found some interesting opportunities with the heterogeneous catalysis and catalytic process. It's called CAPRO in IST under the Center for Structural Chemistry. I look at what they have there, and I feel this is another opportunity for me. And lastly, the Center for Physics and Engineering Materials, I see they have a number of materials for nano fabrications. So I can do some 2D materials as catalysts, especially with the proposal I have on conversion of glycerol into graphene. I look over there, I see that this is a project that is highly doable at the Center for Physics and Engineering of Advanced Materials.
Okay, thank you very much.
Yes, thank you.
Thank you. Any other question or comment on this presentation? If not, I'd like to thank you, Olumide, for this nice presentation. Sorry, we don't have enough time to see all your materials or your slides, but we'll have for sure another opportunity to talk and to try to establish any connection with our department and your research. For sure, we have different teams here, and some of them are also working in plasma, start working in plasma conversion of CO2 using plasma. So it's something that we are developing at our department. So probably in the future you can have opportunities to talk with you and string our relation. So if there are no more questions, if there are someone that wants to make any question or comment,
thank
please.
you. Luisa is reading.
I can see no one asking. So I think we need to close now this DEQTalks. thank you again for have this availability to be with us, and we'll see next time. Okay.
Thank you very much for the opportunity.
Thank you.
Thank
Bye-bye.
you. Bye-bye. Bye.